Hi, this is Evan Yaris. I'm with Design World Magazine, and today I'm with Jennifer Herron from Action Engineering. Jennifer is pretty well known in the industry. She's a CAD and collaboration and integration expert, and she's particularly known as a proponent of model-based enterprise and model-based development techniques. Today she's going to talk about mass properties in the context of large assemblies. So Jennifer, thank you for coming, and why don't you go ahead and start and tell us about mass properties.
Okay, thank you, Evan. I want to start by introducing mass properties. And mass properties for a vehicle are, at the very beginning, part of F equals MA. We need mass in all different areas of engineering to define what we're looking for and make our engineering designs come out with the right outcomes. So when we talk about mass in a CAD system, we say, well, why bother to put it in the CAD system? We do it other ways. And the reason is at a top vehicle level integration, you really need that information to give you moments of inertia so that you can, for instance, on a windshield wiper, you can determine what torque is necessary for the motor that you're going to use. You also need it for a suite of analyses that gets done. So the bottom line is you need M, and what I'm going to talk about today is how you get M into your CAD models in a robust method, in a robust manner. So the question is generally, you need your mass, and you need to get these moment of inertia estimates where we can get the overall mass of the top assembly as one of the variables that we need. We also want to find out center of mass, and we want to find moments of inertia. And generally, again, we want to see this at a top vehicle level assembly or at an assembly and not just the component level. So you generally have a CAD model. It could be in a concept state. It could be in a released state. But generally, I work in the concept area, and we're trying to ferret out what size of reaction wheels, for instance, to go onto this spacecraft, or what size thrusters and propulsion system do we need. And to have that, we're going to need the mass, the moments of inertia, and the center of mass. So I've got this model here, and I have to get all of that information into the CAD system, or into the CAD model, to give me the information that I need and use my CAD system as a calculator. So the way that these mass estimates are done today, I say in the past because I wish that's where it was, we use a spreadsheet, and every single line item component is given a mass estimate. And then it's summed up using a spreadsheet. Clearly, that's a very tedious method. You have to calculate and copy and paste the mass of each component into a large spreadsheet. So it would be much preferable if we could do this all in our CAD system. So again, I got a lot of pushback about why we would do this and why we would put it into the CAD system. There are a few reasons why I advocate it. First, you get a competitive advantage, especially in the concept phase. You can quickly configure your vehicles with accurate mass properties, and your mass analysis is going to consume a whole lot less hours. We have lower mass growth allowances. These are used in the defense and aerospace industry to indicate, depending on the design maturity phase that you are in, what percentage to apply to your mass estimate. So if you're really early in your design process, you might give, a bracket that you think weighs 5 pounds. You might give that a 20% mass growth allowance, and then the predicted mass becomes 20% higher than your calculated mass. So you also get a more accurate concept design. Your analyses is going to converge faster. If we go back to the example of the spacecraft, we can figure out more quickly what the reaction wheels, the sizing of the reaction wheels will need, and then we can work that back into our full system layout. So the other thing is that if you do want to use the spreadsheet, you can still validate that spreadsheet with your CAD model. And I really, really like this method because it does give me kind of a closed loop solution on a bunch of guesswork because you are guessing what the mass estimate is, and I like to get a few more calculations to corroborate that evidence. Okay, so the big question is how, and I want to bring it back around to model-based enterprise. It is very, very difficult to calculate a large vehicle assembly without having good processes in place to apply materials and apply mass to each model, so that then when the whole system comes together at a top level assembly, say your entire airplane has accurate mass applied. So what we need is a modern approach to fully utilize the capability of our CAD software tools. And we're not really doing that yet. There is a lot of great technology available that supports model-based enterprise, but we don't really know how to use it to maximize the benefit or to even support model-based enterprise fully. So there's two pieces. You need a framework to put this together, and the first thing I advocate is that you need a CAD modeling standard for your parts and assemblies, and in that standard you would have things like every time you create a part you apply a material, and that material that you have applied is in a centrally controlled material database, which again is supporting the concept of model-based enterprise, where we're not only reusing the CAD models, but we are also reusing the material database, and it's coming out of a central location. The other thing that is a really great help is to have standard part library, and in those standard part libraries they have accurate mass, size, shape, and accurate CGs. The easy example here I like to talk about is, let's say you have a bolt, nut, bolt, and washer assembly that you need to run down a large structure, and those masses of all those fasteners will eventually add up to quite a large number and can significantly affect your moment of inertia and your center of mass. So I like to have them as accurate as possible instead of just guessing at how much your fasteners will weigh, which many people do, and I have done in the past. Hey, I think this is about 10 pounds of fasteners, and then spread that over the whole system. I like to actually place all those fasteners in the system and have the CAD software just calculate the most accurate mass properties that it can. And it's doing that because it has all the very accurate data to input into the system. So that's the framework that you need. The process to do this is you apply a material or a density to every part. And I do it in that order. The first question you ask yourself is, can I apply a standard material? The second question I ask myself is, well, if I can't apply a standard material, can I assign a mass property? Most CAD systems will let you do this. They will let you assign a mass and assign a density, a center of mass, and even a moment of inertia. And then the second thing you need is a method to represent fasteners and miscellaneous mass. Now, I gave the example of I prefer to use accurate fasteners, but if you are early on in your concept stage and you don't either have fastener locations identified, then you want to come up with a method that is an accurate representation of where that mass might be spread. And I'll give you a visual example of that in a little bit here. The other thing is to maintain those standard parts and any other parts, for instance. Let's say you have a radio that you're putting into your spacecraft, and you decided that that was 10 pounds, and then you got updated information from the vendor and you discovered it's 5 pounds. Well, you need to update that data. Although it seems like a very simple thing to do, those are the kinds of things that easily get lost. You need to update the mass of that part, because we often are just not really thinking about mass at this point. The final thing, and this is a real critical piece of a model-based enterprise and maintaining model-based engineering, is to have an accountability system in place so that all these things get checked. Nobody wants to mess up the design, and nobody wants to have an inaccurate system, but it's easy to do because A, we're busy, and B, we're human. So I like to set up these checks and balances so that people can really have a collaborative experience where everybody is helping everybody with the design, and no one person is stuck trying to validate all of this data themselves because it can be very tedious. So I really am a very huge proponent of a top assembly CAD integrator and/or configurator. This person is the person responsible for the roll-up of that assembly. And for very, very large systems, you may have multiple configurators. You know, if I take an airplane, for example, we'd have a top level configurator, and they will be pulling together 10 different subsystems, all of very large assemblies each themselves. So you might have a structure configurator under that person, and so on. The next thing is, and I cannot emphasize this enough, somebody who is a 3D CAD checker. This is somebody who is a super user of CAD. It's somebody who can really get mired in the details, but can also keep an eye on the big picture. And they're really a second set of eyes for everything. They are the double checker of all the data, form, fit, and functions. Their primary responsibility is to make sure interfaces fit together. And in our case here with mass, make sure that each part has a mass, and that when it rolls up together, that assembly is it seems reasonably good, and maybe even they've performed some hand calculations to corroborate that, because if we just assume everything is going to come out correctly, it's just like any other analysis. We need to make sure that we're double checking ourselves along the way. And the final thing, and obviously this is a hot button for me, standard part librarian. And then again, that's the person who does that maintenance. So CAD software, it doesn't get any more accurate to analyze the mass, center of mass, and moments of inertia. However, it is extremely important that that data is actually in the system. So let me switch over now. And so you should be viewing the SolidWorks screen right now. And in here I have a concept model of a lunar lander. And it's got 3 stages and a final lander. And so what I want to show you is I've got this black and white center of mass symbol in the center. That is indicating where my mass properties are being calculated at right now. And if I click my mass property button and show it to you, what I have is somewhere in the middle of my stage number 2. And I'll kind of highlight this right here. My center of mass is at x equals 41. And you can see the coordinate system, vehicle coordinate system is here. So x is straight up the launch axis. So this is my full stack assembly. What I want to do is switch to a configuration of just my descent stage. And my descent stage, I've expended my first and second stages to get to the moon, and we switch to a stage where the lunar legs are deployed, and I can redo my mass properties. And what I find there is now my X is at 69 inches in the X direction. Now bear in mind my frame of reference has not changed. So that is the original coordinate system is down at the bottom of the stack, the original stack, and so that's why it's showing it up here. But the cool thing there is I'm switching between configurations, and it's automatically giving me this data as it refreshes. So now if I open up the lander, what I want to show you here is I actually have a wet configuration, and in the spacecraft business that means we have all of our fuel is contained, it's a fully fueled vehicle at this point, and so there are our tanks in the middle and it's fully fueled. So I have a particular moment of inertia about the x-axis that I will point out here, and it's at 20.8 kilograms per meter squared. And I just switched units on you just so you know that that's why the x is a little bit different or would seem inconsistent. But SOLIDWORKS does a nice job of switching units and keeping that consistent. So I have, again, 20.8 as my moment of inertia about the x-axis. And what I want to do is I want to, I'm working on this configuration, and I say, hey, I really can't just have 2 tanks. It's just not enough. It's just not enough fuel, so I really need 6 tanks. And I update my assembly, and then I can rerun my mass properties, and you will notice now that because I have fuel and tank mass associated with each of those parts that are in that pattern, I now have an updated mass moment of inertia about the x-axis of 22.3 kilograms per square meter. So it's very cool working concept. This can also, of course, apply to actually coming up with the final configuration of the vehicle. So this is one thing I want to show you is the way I make my fuel tank is that I have a fuel tank, and then inside that, this fuel tank is a hollow shell representing that mass. Inside that, I have a mass allocation for the hydrazine. And I am going to section this for you so you can see inside my tank. I think this looks like chocolate truffle. So, but inside there is this red mass. I make it red, and I don't ever color any other parts red because I want to make sure that I know this is a mass allocation, and this is something that may or may not be adjusted as needed as the assembly changes and as the layout changes and the propulsion system changes. But this mass inside goes with every tank assembly, and that's why the moment of inertia increased pretty significantly, because if it were just the fuel tank, it might not have made as big of an impact. So that's how I do those. If I go back to my lander assembly, what I have here is I have, like I said, the wet configuration, and now the other piece of information that I need to give my guidance, navigation, and control guys is I need to show you what the mass properties look like when it's dry. So I have a configuration for dry. Doesn't look like it changed, but what I've done in the dry case is I've actually suppressed the red mass allocation in the center of that tank, and then we can come back over, and this is even the 6 configuration. We've gone down to 20.7, our moment of inertia around the x-axis. So that gives you a little bit of a feel for how to do mass properties. Now, each one of these components in here, each has a mass applied, or it has a density that represents the center of mass. And so it's a very bottoms-up, data entry consistent system, but once you have it all set up and in place, all this information can be reused. So I did want to mention that let's say you had a bunch of fasteners along these panels and this pylon here, and you needed to estimate them. What I would do is create a shape, a mass allocation shape, hopefully red, that would represent this edge. Give that the mass spread that you think will be applied for those, and then I would duplicate that on every surface, either with a pattern would be adequate, so that you could then rotate that those mass allocation estimates around, and they are going to give you accurate mass properties because they'll be spread at the right locations. Okay, so that concludes that portion of the live example. I will follow up with just one piece of advice here, and that is to understand that CAD evolves as your design evolves, so does the detail in your CAD. And I've got a number of examples here that obviously when we're starting at the CAD idea concept stage, you may or may not be on a napkin, but this particular design started here as a napkin, and then we moved up, okay, well, give me some concept ideas. It's going to be a bunch of slices. They'll be stacked together. And then we went into two different trades. Well, these two different trades don't look significantly different, and they may or may not be significantly different from their mass or metadata or even material stage, but from this quick screenshot graphics view, you can't see any of that detail. So it's very important to understand that because what you see on a quick picture screen looks good, it may or may not have the full detail. And so as your CAD detail increases and as your product becomes more mature, that means all of your metadata, your annotations, even your material definition and mass definition will also evolve. And that's an important concept within the aerospace industry, is that mass evolution, and we have the management of how we do that. So, but again, because we get such great pictures on our screen really quick with CAD models, you have to make sure you don't trick yourself into thinking that all the detail is there indeed. And that is the conclusion of my mass properties presentation.
Thank you, Jennifer. You know, I have all kinds of interesting questions about this, or maybe they're just boring questions. But something I'm curious about is, if you have simplified models, for example, you often don't put in all the holes on something, or you don't tap the holes out in the model. You may not put on all the blends. Do those simplifications really affect your mass properties calculations, or is it good enough for the idea and concept phase, and then they become refined as you evolve the model?
Right. I think that you have kind of answered your own question. So good job. That's exactly it, is as you evolve, those estimates will evolve. Now, at some point, though, you still have to engage your engineering judgment, and it's good news for engineers because I don't think we're going to be put out of a job because of model-based enterprise or engineering processes. It just hopefully makes it easier for us. So the thing to note is, you know, if you are making a very large structure of an airplane, whether you put in 30 thousandths radius on every single bracket is really going to have zero impact on your overall moments of inertia, say when you're doing some landing dynamics or something like that. However, if you're working small medical devices and you have a very small and thin robotic arm, 30 thousandths radius might have a large impact on the mass, and that may affect what kind of motors you're choosing, and then again affect your mass. So it still does not allow us to ignore our engineering judgment, but it does give us a very accurate calculator to use that mass estimate and that geometry together in a large layout.
Kind of a thought that I had related to model-based enterprise is that if you actually have 3D GD&T inside the model, you may have tolerances, and you could actually possibly do a study using tolerances at various upper and lower levels to determine minimum and maximum mass. Would you normally do that with the CAD system, or would you use special tolerance analysis software for that?
I don't personally have any experience. I expect that that level of analysis is immature if it's done at all. But I think it's a really beneficial tool that we could take advantage of tolerance, like you say, minimum and maximum analyses, and be able to use that to more accurately predict mass properties earlier on in the concept phase. The benefit to that, especially for spacecraft, is if you have a very accurate mass property estimating system, you can lower your mass property contingencies, and what that means overall is by the time you get your system completely summed up at the top level assembly, it means I could possibly go on a smaller launch vehicle as opposed to a larger one, which saves a ton of money.
Years ago, I was talking to a fellow named Mike Dinko, who was involved with the early days of CAD, and he was at Lockheed, and he pointed out that on the Lockheed L-1011, nobody could tell you what the distance was from tip to tip of the wings because there was so much tolerance stack up, they simply had no way of knowing. So tolerance can be interesting.
Right.
What is your source of truth normally? You're saying it's a good idea to put this stuff into the CAD file, or even have it in an Excel spreadsheet and a CAD file. Where should the source of truth be? Should it be in a requirements doc or a spec or an email or a PLM system? I mean,
certainly not an email.
It happens. It happens.
I know it does, and that's why I would definitely draw the line. It depends. Now, again, depending on your industry and your system, but for spacecraft and aircraft, those are generally contract-level documents where you will have a not-to-exceed mass. And again, for a spacecraft, the practical reason is because we got to put it on some launch vehicle, and we have to develop that all in a parallel path. So that, though, is your not-to-exceed number. Now, when you say source of truth, I would call that the original data. And my experience has been that me roughly mocking up even some structure is far more accurate than me just guessing out of nothing what that mass will be. And like I said, if we look at this CAD evolution triangle, you start very low with a small amount of detail, and it just expands, in some cases exponentially. So hopefully that answered your question. I mean, again, you'll have a contract not to exceed mass that you are getting to, but that mass evolution over time will be a asymptotically decreasing sine wave because you will eventually approach a solution, but you'll go above, you'll go below, you'll go above, you'll go below, and so you might be able to get to a situation where you don't go above and below, and that path becomes more linear.
I like your suggestion of using a super user that's as a checker, because I don't see any way to maintain consistency if you've got, let's say, your materials spec in a spreadsheet somewhere and making sure that the CAD files have the same materials and that the numbers are consistent from place to place. I don't see an easy way of doing that other than having somebody who is a fastidious kind of power user to check stuff. Do you see any other way?
I really don't. It's been something that I believe companies really fight. Companies have really gone to peer checking, which is ineffective because that's not their primary job, and so they really can't make an accurate, or not an accurate, but they can't dedicate the time to be really thorough. But if that's your sole job, is to be thorough and to be checking all those things, and you have the CAD expertise to go along with it, then you are A, in a very powerful role, but B, you're actually making an impact, as opposed to, I think, where people got to with checkers is that they weren't as impactful as they wanted them to be, and then they were dispensable, which is really a shame.
I think the theory is to have your PLM system be able to do a lot of this stuff automatically, but theory and practice don't often seem to relate to each other. Um,
Yeah, I agree, but I don't think that PLMs are advanced enough to know that you modeled it badly, and so
yeah, that would be
you modeled it
quite a
badly,
trick.
and then your mass properties are inaccurate because of that, and it happens a lot. Torus shapes, for instance, you can make a torus shape, and it's pretty, and I could apply a mass to it and say, hey, yeah, that's great, that's it. Well, torus shapes don't accurately, they don't come out accurate for mass properties, for moments of inertia. So at least that has been the case. Now I'm sure all those things are being ferreted out, but that was the case in the past, and unless, it doesn't know that your vehicle shouldn't weigh 20 million pounds.
Yeah, well, that should be a good clue to you that something is wrong.
Exactly, but the database won't care.
Yeah.
So.
Well, I really appreciate you taking the time to talk about this with us today.
You bet.
That's all the questions I have, and I imagine if other people have questions, they'll pop in on the website and add some comments. So thank you very much, Jennifer, for coming by, and we'll talk another time soon.
You're welcome.